for showing up today. And it's really great to have us here again, another seminar. Today we have Felix, and Felix was originally trained as an evolutionary biologist at the École Normale Supérieure, Paris. I hope I
Yeah,
pronounced that well.
Yes, it's fine. Yes, it's fine.
Okay, sorry about that. But completed his PhD in probability theory at Sorbonne, at a college in France, in Paris. So his research work was first focused on stochastic models motivated by questions arising from population genetics. Since the onset of the COVID-19 epidemic, Felix has been interested in epidemic modeling and recently started his PhD at Quebec,
Yeah,
Université de Quebec
UQAM.
in Montreal on COVID-19, which was partially funded by the MFPH, Mathematics for Public Health Program. So today, Felix will be presenting his work on a general stochastic framework for modeling the spread of complex diseases. So Felix, you're welcome. Thank
Thank
you.
you. Thank you very much, Jimmy, for the invitation and introduction.
You're welcome.
So I guess this meeting is also the opportunity for us to get to know a little more each other. So just a few other words about me. So as Jimmy was saying, I really did my undergrad like in pure biology and then started doing some more theoretical stuff related to evolutionary biology. And then I completely switched to math. And so I did my master's degree in math and my PhD in math. And so now I'm kind of sitting in between applied math, where I'm really interested into like applying stochastic methods to understand some biological phenomena. But I'm also just interested into, well, you could say pure math, just like purely probabilistic aspects of population models. Okay, so today I'm maybe going to insist more on the modeling aspects of my work. And so what I'm going to present is not something that I've done during my postdoc because I've just arrived in Montreal, but it's something that I've done during my PhD. So when I was in Paris. Okay, and so it's something that it's a project that we initiated with my research group at the time that was called the SMILE group, and which is led by Amaury Lambert. And I also want to mention the name of my other PhD advisor who was very involved in this project, who is Emmanuel Scherzer, and who is now in Vienna. Okay, so the work that we did is that we wanted to propose a new class of models that are stochastic, and that in a sense generalize the usual approach to epidemic, which is based on ODEs and on Markov processes. Okay, and I'll come back to that in a second. And the objective of my presentation today is first to introduce you the class of model that we have considered, and then just also really discuss how, even if these things are a bit more complicated than the usual framework, to really insist on the fact that they can be used in applications and in real data. And I also try to compare what we did with existing approaches. Okay, so for this reason, for the next couple of slides, I'm just gonna start slowly and try to recall what, at least to me, is like the classical way of modeling an epidemic, both on the stochastic world and on the ODE world. Okay, so also, I do not know the background of the people here, so I do not know how much you are familiar with stochastic techniques. So please feel free to interrupt me if anything isn't clear, or if there is an object that I've not introduced and that I'm assuming that you know, but you don't know, just like interrupt me and I just discuss that. I don't mind not going until the end of my presentation. Okay, so, well, Epidemic 101. I'm gonna illustrate all of, okay, so in order to illustrate how the work that we did is different from the classical approach, I'm always going to take the simplest of all examples, which is like the SIR model. Okay, this is going to be my toy example from which I discuss like the more general concepts that I need. So so you all know, of course, the SIR model in the ODE world, but you can actually define an object which is the stochastic version of the SIR model. And formally, this object is actually a Markov process with valued in the integers to the cube. and I'm going to call its coordinates. Okay, so it has 3 coordinates. I'm going to call the coordinates S, I, and R, of course. And this, the first coordinate is meant to represent the number of susceptibles, so it's an integer, the number of infected and of recovered, of course. And so the rules of the process are the following. So I'm going to start from an initial number of individuals, which is fixed and which is given by some parameter n. And then the process will, okay, so it's a Markov process in continuous time. So time here is continuous. So it's a process that will actually jump, and the distribution of the jumps are the following. So we can only see 2 types of jumps. So the first one is that you lose a susceptible and you acquire an infected individual. So that's just an infection. And I'm going to say that infections occur at a rate which is beta, which is just the per capita infection rate in the population times I. And so that's just like the total number of infectious particles that individuals produce. And for that to give an infection, you need to select, you need to make contact with a susceptible individual in the population, and you make contact with a susceptible with a probability which is S divided by N. Okay, and so second type of transition, now I lose an I individual and I acquire an R individual, and that occurs at a rate which is gamma times I. So this just means that every individual at rate gamma is gonna become recovered. Okay, so just, is everyone like familiar with Markov processes in continuous time? So when I say that it jumps at some rate, is it like clear for everyone what it means? Okay, so very briefly, it means that I just wait for an exponentially distributed amount of time, and I can compute the rate of the exponential distribution according to those rates. Okay, anyway. Okay, so now first result, which is quite classical in the probability literature, is that if I let the size of my population go to infinity, then I can, my Markov process is going to converge to something which is deterministic. Okay, so very briefly, suppose that now I start from a large number n of individuals, and I assume that there is an initial fraction x naught of individuals that are infected, and that all other individuals are susceptible. Okay, so I don't have any recovered individual at time 0. And now suppose that I rescale my process by 1 over n. So this means that now instead of counting a number of individuals, I'm looking at the density of individuals that are susceptible, infected, or recovered. Then if I let n go to infinity, this Markov process converges in a sense towards a limiting object. And this limiting object is actually a deterministic function, which turns out to be the solution to the very well-known SIR set of ODEs that you are all aware of. Okay, and so now the meaning of this convergence step is that this convergence occurs in probability for the uniform norm. And what this means is that with a very high probability, with a probability that goes to 1, my Markov process, which is now seen as a random function of time, okay, I look at all the trajectory of my process. Well, all the trajectory is going to be within a very small neighborhood of the solution to the stochastic, sorry, to the deterministic SIR model with very large probability. And so this kind of results, we call them functional laws of large numbers. So a law of large number because we have a limit which is deterministic, which is just an ordinary differential equation, and functional law of large number because the way that we have a convergence is a functional convergence. Okay, we really have convergence of functions. Okay, so just maybe to illustrate that result. So now I've represented, so the light shades correspond to actually simulations of the SIR model, and the dark shade, the dark black solid line is corresponding to the numerical simulation of the deterministic SIR model. And you see that for even for n is equal to 500, the deterministic curve is actually quite a good approximation of the stochastic trajectories. And now if I increase the population size, you see that now things are getting more and more concentrated around the deterministic limits. And if I even increase even further n, then you are not able to distinguish between like the stochastic model and the deterministic ones. So what I want to illustrate with that is that there is this interplay between like stochastic models and deterministic models, and that deterministic models actually correspond to the large population size limits of some stochastic models. And also, I want you to see that actually this limit kicks in quite rapidly, because even with 500 individuals, the deterministic equation is quite a good approximation of the stochastic one. Okay. So, okay, so now I wanted to show you that because I wanted to make the point that if you are using an ODE model, okay, so now I'm just speaking generally, okay, I've taken the SIR model, but I could have taken basically any model of the ODE type. And so if you are taking some ODE type of epidemic model, then what you are actually doing is that you assume that you have a discrete population, so an individual-based model that is underlying your set of ODEs, and that you consider that you take a large number of individuals so that you can approximate the stochastic model by a deterministic one. And this means that when you are using an ODE model, you actually assume, in a sense, that at the microscopic level, the process that describes the infection between the individuals is a Markov process. Okay, so there's really a tight link between having a limit which is described by an ODE and being a Markov process in the first place. And this means that at the microscopic level, actually, due to the Markov nature of the stochastic process, it has a lot of constraints. Okay, and so in particular, a consequence of being Markov is that the time that you stay in each compartment is an exponential distribution. Okay, and also the time that you need to wait before seeing two infections from the same individual is again going to be an exponential distribution. So, okay, so I'm not trying to criticize the ODE models, because like the ODE models are great, they're extremely flexible, they are they have provided a lot of very interesting results. But just it's nice to keep in mind that they rely on some microscopic assumption that we are not that sure of. Okay, we do know that some time that you stay, for example, in hospital is probably going to be bell-shaped and not going to be an exponential distribution. And again, the time between the consecutive infections, you're probably going to have an exposed phase, a latent phase before you see a lot of infection, and then it's probably going to be peaked again. Okay. And so what we wanted to do with this work was to see if actually we could design a model where those two assumptions at the microscopic level are not met. Okay, so what if we just remove the assumption that we have a Markov process? And now, can we still say some things about the model? So does it remain tractable? And if yes, that's nice, because this means that we actually have a new set of models that we could use. Okay, I'm not saying that those models are better than ODEs, but just that maybe in some cases, it's nice to have more choices. Okay, anyway, this was our initial motivation. So just like trying to relax those Markovian assumptions. And this is also an interesting question from the mathematical point of view, because it's probably going to give rise to more interesting behavior, because Markov processes are very constrained objects. Okay, so anyway, here's what we have done now. Okay, so in the next couple of slides, I'm going to explain the model. And so please do interrupt me if anything isn't clear, because I'm not going to come back to it afterwards. And all what I'm going to say after that is going to rely on those few slides. Okay, so first I'm going to describe at the level of one individual, what's the course of the infection at the level of one individual. So first assumption that I make, which is just a very classical one, is that at any time, at any point in time, if I look at an infected individual, then I can, it belongs to one of several states that we usually call compartments, and that represent usually some clinical states. Okay, so any individual at any time, I can put it in a box, and this box I call it a compartment, and it represents in what state it is. So for instance, for the SIR model, the set of compartments is only going to be an infectious compartment and a recovered compartment. Okay, so I always exclude susceptibles. So I always assume that there are some individuals that I've not seen the disease yet. The compartments, I only focus on the compartments once you are infected. Okay, and I treat the recovered compartment as any compartment. Okay, and so for a COVID-19 model, typically you will need to add a lot of compartments because we know that COVID-19 is a very complex disease. Like you have pre-symptomatic transmission, you have a whole range of symptoms going from like asymptomatic to middle symptomatic to like being in ICU. And so typically you will want to add some, for instance, a hospitalized compartment, an ICU one, a dead compartment, and whatever you want. Okay, so now for each infected individual, so I consider a focal infected individual that I denote by K, I'm going to record the sequence of compartments that it will visit during its infection, during the course of its infection. And I'm going to record it as a stochastic process that I denote by X sub K of A. And so the interpretation, so A is a real-time parameter, and the interpretation of X sub K of A is that it's a random variable which is valued in C, and this random variable is giving me the compartment of individual K at age K. And so from now on in this talk, when I say age, I don't mean the actual age of an individual, I mean what we call the age of infection, and this is just the time elapsed since the infection. Okay, so this is just a terminology that comes from the world of like general population models where an infection can actually be interpreted as a birth in a population, and then the time which is elapsed since the infection is just the age of the individual in this like population interpretation. Okay, anyway, see if, for example, xk of 10 is equal to hospitalized, this means that 10 days after its infection, individual k will be in hospital. Okay, and so now I have this knowledge, but for all time a, okay, for all ages a. Okay, so again, I'm gonna illustrate that with the SIR model. So in the SIR model, when you get infected, you can only be into two states. Either you are infectious or you are recovered. And when you get infected, you are automatically infectious, and you stay infectious for a time which is exponentially distributed with some recovery parameter gamma. And so this means that in this formalism, the process xk of A is nothing but a process which has only two states. First, it is in state I for a time from 0 to t, where t is some exponential random variable. And then it jumps to state R for a time which is between, well, t and infinity. Okay, it remains in R indefinitely. Okay, so now I suppose that xk of A is giving me the sequence of compartments that are visited by an individual, but I want to record a second thing about individuals, which are at what point in time is this individual going to infect new people. Okay, and so this second information, I'm going to recall it as an object which is called the point process that I denote by P sub k. Okay, and so P sub k now encodes the moments when k will make infectious contacts in the population. So mathematically speaking, P sub k is what we call the point process. And so this is defined as a random measure, which is purely atomic. Okay, so if you are not familiar with measure theory, then you are even less familiar with the theory of random measures. Then in that case, you can maybe see P sub k as a random vector with a random length. Okay, so here, for instance, the vector has length m, and m is a random variable. And then the first coordinate is a random variable that I denote by a1, and so on and so forth. Okay, but actually it's more convenient to view it as a measure, which is just obtained by putting a Dirac mass located at each of the AI. Okay, so I'm just going to represent this point process in the following way. So actually a point process is just a way of putting points on the half line, okay? And so those points, I represent them by those gray circles. And the interpretation of this picture is that 0 is the time when individual k gets infected. And then a1 unit of time after being infected, individual k will infect someone else in the population. And a2 unit of time after being infected, it will infect a second person, and so on and so forth. And in total, individual k will have infected capital M individuals, and the location of the atoms just gives the times at which it has infected the people. So again, in this SIR toy example, we have said that individuals can only infect new people when they are infectious, so when they are in the I state. And when you are in the I state, you produce new infections at a rate which is given by some parameter that I have denoted by beta. And so this means that the infection point process is going to be nothing but a Poisson point process with intensity beta. Okay, this means that you have atoms that occur after exponentially distributed amount of times with rate beta. But now I have to restrict this Poisson point process to the period of time when PK is infectious. And this I had denoted it by T. Okay, T was just recovering time for individual K. Okay. So now I suppose that I have this pair xk pk for each individual, and I assume that when I know xk and pk, this describes me perfectly the course of the infection of individual k. Okay, I know in what compartment it is, and I know when it has infected new people. And now I have to give me some rules on how infection is spread from one individual to another. And so now I'm going to do something which is very similar to an object in probability, which is called a Crump-Mondiager process. Okay, so a Crump-Mondiager branching process. I've just put a reference here for these objects. And the rules of the model is the following. So I'm always going to consider that the population size is fixed to n, as in the SIR model. Then I'm going to make a very important assumption, which is that the pairs PK, XK are IID. So in practice, this means that whenever an individual gets infected, I'm just going to sample the course of its infection independently from the rest of the epidemic. It means that infections between different individuals are actually identically distributed replicates of the same typical infection course. Okay, in particular, it does not depend on who has infected you, or if like there is someone infected in your neighborhood. Okay, it's all IID. I think that's not a big assumption. Okay, and I just want to insist on the fact that it's the pairs that are IID. Okay, and that PK and XK are not independent. For instance, in the SIR model, you could only infect people when you were infectious. And this means that the two are not independent. And actually, I've made no assumption about PK and XK. Okay, these are just like totally general. Okay, so now, whenever an individual makes an infectious contact, this means that whenever you have an atom of the infection point process, then this contact is going to be made with an individual in the population, and that individual is going to be chosen uniformly at random. Okay, and I'm going to denote the label of that individual by K. Okay, so now this is a very strong assumption. Okay, it's a mean field assumption. So I'm assuming that I have no precise contact structure. Okay, so for instance, I cannot account for people that live in the same house or this kind of things. Okay, everyone is equally likely to interact with everyone. Okay, that's quite a strong assumption. I just say in a few words at the end how I can relax it a bit, but yeah, I agree if you are saying that this is quite unrealistic. Okay, so now suppose that you have an infectious contact. You've decided who you are making this contact with. It's capital K. And now there are two options. Maybe capital K is already infected. Then nothing occurs. Okay, I suppose that immunity is non-vanishing, and I suppose that multiple infections do not interact. Okay, once you've been infected once, then you cannot be reinfected again. So now if K is susceptible, and assume that this contact has occurred at a time which is given by T, then I'm going to infect K with a probability which is given by C of T. Okay, so if C of T is equal to 1, then this means that whenever a susceptible is hit by an infection, it just becomes infected, and that's all. And what I want to model with this C of T is some time heterogeneity, which is typically the enforcement of some control measures. Because for instance, if at some point in time, the country enforces a lockdown, then it is very likely that some contacts that should have been made in the population are not made because people are constrained to stay at home, okay? And this means that I'm reducing the contact rate in the population by a factor which depends on time and that I denote by CFT. Okay, that's how I'm going to incorporate time heterogeneity in the model. Okay, so now maybe a graphical illustration of what I've just said. So time is going upwards. I'm representing individuals in the population by those vertical lines, okay? And suppose that I start with 2 infected individuals that are represented by those black vertical lines. And then those individuals come with an infection point process, and I represent the atoms of this point process as those gray dots. So now what I do is that I take the first atom, which is this one, and I'm going to select an individual uniformly from the population. So suppose it's this one. So this one individual was not infected before, and then it becomes infectious, it becomes infected. And when becoming infected, it comes with its own Poisson point, with its own point process. And this point process is actually an IID copy of the point process of the typical guy in the population. Okay, and so now I've taken the smallest atom. Now I'm taking the second smallest atom. Again, the infection is targeted to a uniformly chosen individual and it becomes infected. And now I can just like iterate this procedure. And so the 2 things that I was saying is that sometimes some infections are ineffective, and that's because there's been some control measure that has been enforced. And sometimes you are going to target an individual that was already infected in the past, for instance, here or here, and then nothing occurs. Okay, so that's all for the model. So now I'm just going to, so if you have questions about the model, which would be quite natural, just like please ask them now, because from now on, I'm going to study like the mathematical properties of this model.
I've got a question.
Yeah, sure.
I put it in the chat. I was just wondering.
Sorry, I don't see that.
On the previous slide, is C of T dependent on the infector's stage of infection?
Well, actually, there is no infector stage of infection. I mean, I completely uncouple the stages and the infections. Okay, I just say I have some moments of infections and I have some states. But I do not assume that there is a strict infectious period and that I cannot infect people outside of this period. This is a possibility. I mean, you could totally do that, but I do not restrict myself to this case. I'm sorry, I'm not sure to have understood your question.
So basically, I was wondering if, in one sense, is there say a latency phase where the person is infected but not infectious, or is this kind of a thing where the probability goes in discrete chunks, depending on what stage they're in, or is it a gradual thing? That kind of question.
Okay, so you could do that in principle. So if you wanted to do that, okay, I'm just going to go a couple of slides backwards. For instance, if you want to have an SIR model, then you will just incorporate an exposed phase. Okay, you're going to say that I start with an exposed phase, then I move to an infectious phase, and then I move to recovered phase. And then you will need to transform your point process accordingly so that you only see infection during the infectious stage, okay? But here's this T of T is something a bit different. It's something which is like global to the population. It's something which is like nationwide, if you want, okay? It's not something which is local to an individual.
Felix?
Yeah.
So I was actually thinking we'll have question after the presentation, but it's fine because so that we keep to the time, but it's fine. So I have a similar question to what Martin said. And the question was, I was a little bit confused about the C of T, and I was thinking because when you have contact with an infected person, then infectious person, then there is a probability of infection, right? And the contact should be different from the probability of infection. So I was thinking, is C the probability or the contact rate?
Yeah, okay. So I assume that in my process PK, I only retain, so okay, I've called it an infectious contact, but maybe I should call it like an effective contact. Okay, if I have a contact with someone, but it's not leading to an infection for any reason, I do not count it into PK. Okay, I've already removed it.
Okay.
Yeah, what I'm trying to model with C of T is more of the like, say for instance,
those that had contacts and were infected.
Yeah, say for instance, now you have to wear a mask, and this
Okay.
reduces the probability that you transmit the disease by 50%. Then at the time when people need to wear a mask, I put C of T equals a half, because I know that this is going to prevent half of the infections.
Okay.
Okay, so for instance, if you install a lockdown and only a fifth of the population is able to live and to move, then I'm going to put C of T is equal to a fifth. Okay. But it's not a very good way of modeling things. It's just that we really wanted to have a way of having some time heterogeneity, because we were really interested into the impact of lockdowns and so like stop and go strategies. But I agree that it feels wrong in some sense, and that we should improve that.
Yeah, it's fine. Then I understand here that C changes with time.
Yes.
So
yeah, time and not of age. Yeah, that's maybe
okay.
Okay.
Yeah. So we have a couple of questions here, and one was from Lawrence. So the question is, will you complete the spreading speed? I guess you understand that.
Yeah, I'm not sure to know what you mean by the spreading speed, but if you mean the initial exponential rate of the population, yes, then this is well known. Yeah, but it's well known for 30 years. It's not my work.
Okay. And another question is C of T same for all PK?
Yeah, it is
the same.
It's something which is global to the population. I really assume that.
Okay.
Yeah.
So in the case of an heterogeneous mixing, C of T should be different for all ages, right?
Yeah, exactly. So you could actually, so I've presented a one-dimensional version of the model, but you could just like extend it to have a multi-dimensional version, like you have patches with a finite number of them, and then you could have like a different C of T for different regions, and you could have like different contact rates in between the regions. That's something that we can do. I'm just like presenting a very simple
one. Okay, the simpler, yeah, great.
Yeah, simpler
case. Then one from Jesse.
Yeah.
Jesse, do you want to ask in person or I read here?
It's okay. It was mostly a follow-up from actually what your question was, which was that another interpretation of PK could be the conditional probability of when an infection will occur, given that it will occur. Is that one way to think about it?
So PK is not really a probability, it's a measure. It's a measure which doesn't have mass one in general. It's just like recording the times when you make infections. Yeah, I'm not sure to see where conditional probability comes into play here. But sorry, I might have not understood your question.
That's okay. I think you answered it. I think it was my misunderstanding then. It's like,
okay, sorry.
It's a distribution of when and also how many additional infections. Yeah. So it's kind of multiplied already. Okay.
May I ask?
And and the when is going to be the locations of the atoms.
Okay. All right.
May I ask a simple question about the mean field?
Sure.
Yeah, how is the mean field assumption plays a role here?
Well, if you assume that you have like a fine contact structure, so for instance, if you assume that your individuals are on a graph and that graph represents the contacts, and that you can only make contact with the people that are in your neighborhood in the graph, then you lose this mean field assumption, okay? Okay, so it will come into play when I will state my results, because my results won't hold if I do not have this mean field assumption. But for the moment, it makes no. I mean, we could totally define the model, but with like a graph structure, but then it would become intractable from a mathematical point of view.
Okay, so this is a very nice formulation.
Answered your question.
Yes. It's a very nice formulation, probabilistic formulation, but there are many assumptions, and the question would be, if I modify these assumptions, you expect very different results?
Okay, so first of all, I think that there is not so much assumption. Like the only real assumption is this mean field assumption. Then what I'm just saying is that if I look at an individual, I can say when it will infect new people and in what state it is. The first one is PK, the second one is XK, and then I put no assumption on XK and PK. If you give me any epidemic model, I could actually tell you, okay, PK is that, XK is that. The very strong assumption that we make is this mean field assumption. And I cannot relax it. I can relax it slightly by saying that I have patches, that I have like, say, some number, but a finite number, well, maybe a countable number, but I'm not even sure I can do that, but at least a finite number of groups, okay, which can represent, for instance, real age classes, like the young, the old, or for instance, cities or whatsoever, and that may contact at different rates, that I can do. But if you have a very fine structure, for instance, like household structures or like graph structures, then everything is breaking down in the model. I mean, you could run simulation, but the things that I'm going to present in a second won't hold.
Okay.
Thanks. So Félix, I will suggest we have some more questions after the presentation because of time. Okay. Yeah. All right. Thank you.
Thanks.
Yeah.
Okay. So let's go to math. So in the SIR, like models, what we do is that we have compartment counts. Okay, what the things that we bookkeep in the model is how many people are in the I state, how many in the R state, how many maybe in the E state, whatsoever. But if we do that in our model, that as the model lacks this Markovian hypothesis, it's not going to be something nice to work with. And so we have to kind of switch point of view. And for each individual, instead of recording in what compartment it is, we have to record its age. Okay, so for each individual, I'm going to record since how many time does this individual when was this individual infected? Okay, so for instance, if I was infected at time, say 10 days ago, I'm going to record for me the 10. Okay, I'm going to record the age. And a convenient way of doing that is to view the population as, again, a point process. So again, as a random measure, okay? And the measure is obtained as follows. So here, sigma k denotes the infection time of individual k. So I'm assuming, I'm looking at all individuals in the population, okay, there are n of them. And I'm only looking at those individuals that have been infected before time t. Okay, so I'm really looking at the population at time t. And now I put a Dirac mass, which has two coordinates. So the first one, t minus sigma k, is nothing but the age of the individual. Okay, so if I have been infected at time sigma k, t minus sigma k is just the time elapsed since I was infected. And in my formalism, xk of t minus sigma k is just the compartment in which I am at time t. So what I do is that for each individual that was infected before time t, I record its age and its compartment. Okay, and a convenient way to record it is to view it as a measure once again. Okay, so now another notation. So in the limit, things will depend on what is known as the intensity measure of the point process PK. And so now this is defined as a deterministic measure. It's not a probability measure, it's a deterministic measure that I denote by tau. And it can be defined implicitly through this formulation. Okay, so if I evaluate my measure against some test function, I get this expression. And if you're not familiar with intensity measures, what tau of A is, tau of A should be thought of as the mean number of infectious contacts that are made when an individual has age A. So it's sort of the infectious profile of an individual. Okay? It tells you, you've all seen like those profiles, like at first you are not infectious, then you have a peak, and then you are not infectious because you've recovered. Then this profile is tau of A. Okay, and so lastly, I'm gonna state a law of large numbers. And so I need to start from a larger number of individuals. Okay, so I'm going to assume that there is initially a fraction x naught of individuals that are infected. And since I'm recording the ages of the individuals, I'm going to have to assign to those initial individuals some ages. And I do it in an IID manner so that the initial ages are distributed according to some probability distribution G of A. So now under those assumptions, here is the main result that we were able to prove. Okay, so we actually proved two versions of this result. So we proved it in a first preprint under the simplifying assumption that susceptibles are in excess. And then like the proof of the result that I'm showing is a bit more involved from a math point of view. So we've written another preprint just with the proof. Okay, so now what we do is that we fix some time t and some compartment I. And as in the SIR model, what we do is that we renormalize the population by n. This means that now we are looking at densities instead of individual counts. And so this renormalized measure is going to converge to a limiting expression. Okay, so the sense of the convergence is that on the set of measures, I use the topology of weak convergence. This is now a new metric space. And now I consider my measure is just like a random element in this metric space. And I take convergence and distribution for this metric space. Okay, anyway, I'm going to state some easier consequences if you're not familiar with this kind of stuff. Okay, so what's interesting is that in the limit, again, we obtain a deterministic expression. So it has two components. So the first one, I'm going to come back to it in a second. And the second one, so it's NT of A. And actually NT of A is, in the limit, the density of individuals at time t that have an age of infection, which is A. And then you multiply it by the probability that a unit of times after its infection, an individual is in compartment I. And this gives you the measure, the limit of the empirical measure of the population. Okay, so now what's interesting is that we have an expression for this NT of A because it is the solution now not to an ordinary differential equation, but to a first order partial differential equation, which is the following. So it's a partial differential equation in the plane, so in the quarter plane, upper right quarter of plane. So first you have like a differential term, which is not very interesting, okay? So if you recall that NT of A is in the limit, the density of individuals at age A at time t, then this term is just telling you that age is increasing linearly with time, okay? So if I have an age, say of 10, and I wait for 5 days, then my age is 15. That's all what this term is telling me. So now we have two boundary terms. So we have two boundary conditions. So the first one, which is again not very interesting, is the temporal boundary condition. And it's just saying that at t equals 0, you have a fraction x naught of individuals that are infected, and their ages are distributed according to g. Okay, nothing surprising because this is how we have initialized the population in a sense. And so now the second boundary condition, which is like the most interesting, is an age boundary condition. Okay, and so if you recall the interpretation of the age, having age 0 means that you have just been infected. So NT0 is just the number of new infections in the population. And so how do you compute it? Well, it's a product of three terms. So this first term, so tau of A recorded is like the intensity measure of the point process PK. And so this means that this is the mean number of infections made by an individual when of age A. And this is the mean number in a way of individuals with age A. And so if I integrate this expression, this is just the mean, not the mean, but the limiting number. Yeah, it's like the average number of infections that are made in the population at time t. And now for an infection to be effective, there were two conditions. So the first one is that you should target it to a susceptible individuals. And this is this factor S of t. Okay, S of t is nothing but the number of susceptible individuals. It's just like 1 minus the number of infected individuals. And so there was a second condition that was like this heterogeneity, this time heterogeneity as C of t. And so we have the product of those three terms. Okay, and so I should have maybe put a reference, but this equation is actually quite well known because it was proposed in the very first paper by Kermack and McKendrick in 1927 as a model for the spread of a disease, of an epidemic. And so it's sometimes referred to as the Kermack-McKendrick model. Okay, so this describes the dynamics of the age structure of the population and is given by a PDE. But now, in real situation, we don't care about the age structure of the population. That's not something that we can observe. Okay, we cannot say for an individual when it was infected precisely. What we can observe are the compartments: who is in hospital, who is infected, who is infectious, and so on and so forth. And so, an interesting corollary of this convergence results is that now, if I look at the number of individuals in compartment I at time t, because for instance, if I is the hospitalized compartment, then Ni of t is just the number of individuals which are in hospital at that time, at time t. Well, I have to make some mild assumption, but really it's nothing big. It's nothing big. And under those assumptions, the previous result actually shows that this converges again in a functional sense towards a limit. And this limit is actually quite nice. It means that if you want to know the number of individuals, say, in hospital, what you need to do is to ask how many people are of age A, and then for an individual of age A, what's the probability that it is in hospital? And then you integrate that and you get just the total number of individuals that are in hospital. Okay, so we have a very nice expression in the limit for the number of individuals in the various compartments. Okay, so maybe I'm just going to repeat myself, but I'm just going to state some consequences of these results. So first of all, what we have shown is that even though the model is stochastic, when we look at it at a large scale, it becomes deterministic. Okay, so we have like some sort of law of large numbers, which is present here. Okay, and so in the limit, the age structure is described by a PDE, and the PDE only depends on this quantity tau. So now tau, I can always write it as R naught times nu, which is a new measure. And R naught is just the total mass of the measure tau. And nu is just like tau renormalized by R naught. Okay, it's just like the probability measure associated to tau. And I've not denoted this by R naught for no reason. It's just because as tau of A is the mean number of infections when you have age A, if you integrate against A, then this is just the total mean number of infections that are made by a typical individuals in a fully susceptible population. Okay, that's just like the usual R naught. So that's something that we can actually estimate, or that we want to estimate. And this new measure here is actually something which is quite well known also in epidemiology, and which is known as the distribution of the generation time. Okay, and so just for instance, for the COVID-19 pandemic, I think in March, there was already 2 estimations of this measure nu that were provided in the literature from the Chinese data. So that's really something that we can access. So that's nice because the PDE, even though it's a PDE, it relies on parameters that we can access actually. Okay, then a second crucial quantity was like those marginals. Okay, the probability that given one point in time, you are in hospital. That you can also directly estimate them if you have like patient trajectories. Okay, so if you have like hospital data where you know that, oh, Mr. X was admitted to hospital at that time with that symptoms, and then he got moved to ICU at that time and he passed away at that time. Then if you have a lot of those data, you could just like build an estimation for this quantity. If you don't, as was our case when we worked on that project, you could just like parameterize it by saying that, okay, with that probability, I go to hospital, I stay there for that amount of time, and so on and so forth. And then you can just estimate the parameters from the data, from like counts. Okay, and so last quantity that's important in the limit is the initial age distribution. And that's actually a real problem because there is no way that we can access the initial, the distribution of ages in the population. Okay, that's really not something that we can estimate. But fortunately, if the large population size that I need so that I can have a deterministic approximation, if that large population size is the consequence of the natural growth of the epidemic from a few infected individuals, which is basically the case, then actually the distribution of ages is shaped by the natural growth of the epidemic. And I have an expression for that. Okay, I can give an expression for that. So this is not a big issue. Okay, so I think I have to skip a part of my talk, but that's really not an issue. So just very briefly, this might seem quite not abstract, but it might seem a lot more complicated than just like using ODEs, and you are right. But it turns out that this is really an extension of the ODE models. Actually, if you give me an ODE model, I can always select the right tau and the right probabilities in such a way that I recover the ODE model. Okay, and I'm just going to illustrate that very simply with the SIR model. So recall that tau of A is just the mean number of infections that you make when you are of age A. And for the SIR model, we know that people infect at a rate which is beta as long as they are infectious. So when you are of age A, you have a probability which is just exponential of minus gamma A of still being infectious, in which case you infect at rate beta. So we just take this expression for tau. And now, as in 2 slides ago, if I denote I of t to be this integral, so what I do is that I look at individuals of age A, and I look at the probability that an individual of age A is infectious. I do the same for R. Now, this is the probability that an individual of age A is recovered. And I denote S as the remaining number of individuals. Then I can show that actually our SIR are the solution to the usual SIR sets of ODEs. And so this fact that the age structure model PD actually is a generalization of the sets of ODEs was actually already contained in the very first paper by Kermack and McKendrick on this subject. And actually, if you go back to this paper, it's quite interesting because I think the paper is something like 10 or 15 pages long, and there are like 2 pages on the sets of ODEs. Okay, they just say, actually, they just introduced this very general framework, and they say, okay, if we make restrictive assumption, then we have this set of ODEs. And it's fun because now everyone is just citing them for the set of ODEs, whereas it was not the point of the first paper. But anyway.
Félix?
Yeah, I think I stopped there. Right?
Not really. Can you round up in 3 minutes or less?
Yeah, I just wrap some things up in 2 minutes.
Right.
So, okay, first of all, just as a proof of concept, we just did some like parameter estimation and model fitting on French data, and you see that the points are real data and solid lines are the best fits. And you see that we can actually reproduce quite complicated shapes of a lot of time series at the same time. And so just wrapping things up, so I've just tried to introduce a quite general individual-based model in which we can just incorporate as many compartments as we want, and we can really have a strong correlation because we have just liberated ourselves from the Markov hypothesis. Okay, I've just forgotten a word there apparently. Okay, then I've shown that in the large population size limits, the age structure is given by a PDE, and this is nothing but the Kermack-McKendrick PDE from 1927. And if you want to have compartment and not just the age structure, you need to integrate the age structure against some probability. Okay, and we said that we are decorating the PDE, and I believe that this was not, well, I've not seen it in previous papers. So this is maybe a contribution of our work, but I'm not sure about that. Okay, and so the limiting equation has 2 features which are nice. First of all, it's a generalization of the usual sets of ODEs. And that's not a surprise because the stochastic model is a generalization of the Markov models. So it's not surprising that in the limit, we've got a generalization of the ODEs. And also, even though it might seem like a very big machinery, actually computations can be made quite efficiently, and they can be made efficiently enough so that we can do some inference and some parameter inference. Okay, and so I had a second part on like doing some contact tracing data to estimate mu, but I'm not going to talk about that. So thank you for attention, and I'm happy to take questions if you have some.
Thank you so much, Félix. That was really great. That was a great presentation. Thank you, thank you, thank you. That was a lot of information in one piece.
Yeah, sorry.